you, Professor Matsumaru, Ohayou gozaimasu, and thank you for all of you coming to my lecture. The title of my lecture is Robotics Research at IIT Delhi and DeNOC-based Dynamics of Robotic System. DeNOC is the name of a method to do the dynamic modeling, which I started about 20 years ago when I worked with Toshiba and when I met Professor Matsumoto there in the company. I wrote here 9 in a series because I give it to different places about these topics, and this is the 9th time for since 2012. So, with introduction about my studies in India and abroad. I studied in NIT, it's called National Institute of Technology, Durgapur, it's the east part of India, in 1983, my undergraduation. Then I did masters in IIT in Kharagpur, also in the east part of the country. We have many IITs. I will give the introduction later. Then I went to Canada, McGill University for my PhD. I finished in 1991. Then I came to Japan to work for Toshiba R&D Center in Kawasaki from 91 to 95. Then I returned to India, IIT Madras, which is in the south of the country, as a visiting faculty. And then I moved to Delhi in 1996, and since then I am the assistant professor when I started with, and now I am a professor there. So that was the brief history about this seminar, this topic. I have given to the following places, USA, China, Japan, South Korea, and of course in India. So today I am here in Waseda-IPS to give the lecture on the similar topic. So my plan of my presentation will be as follows. I will introduce my 2 laboratories where I am doing research. The first one is called the Program for Autonomous Robotics. We call it PAR. And the second one is the Mechatronics. Then I will talk about this will take about 20 to 25 minutes to tell all the research which I wanted to tell you today. Then I will talk about briefly about the dynamics of serial systems like industrial robots, and then the software we have made in 2009. The pamphlet of the software has been distributed to you. It's called RoboAnalyzer software. I'll explain that. Then we move to more complex robotic systems like working robot. We call it the tree-type robot. And there also we have a software in MATLAB. We call it ReDySim. These days when I go abroad, even though foreigners may not speak English, when they hear me from India, they will say, oh, IT. That means you are strong at IT, information technology. So I wanted to encash that aspect, that we are good at the math and the software, so I'm also strong in the software. So RoboAnalyzer is independent of any commercial software. This of course depends on the MATLAB, but if you don't have MATLAB, still you can run. So we have made that arrangement. Then we move to closed loop systems. Parallel robots are closed loop systems. But I have an interest to apply that robotic knowledge for village applications, the rural applications. I'll give a small demonstration for about 2-3 minutes on this. So talking about the IIT concepts in India, you can see now it's almost about 23 IIT will be soon. But originally, for first 30-40 years, we had about 7 IITs, and IIT Delhi is one of them. It started in 1961. Then 2005 onward, the new IITs, red IITs, and one of the IITs has a Japanese collaboration in the southeast coast of India, and the 7 has been declared recently by the new government, which will start soon, so that whole India will have almost one IIT every province, and these are called the centers of excellence like MIT in America. Talking about IIT Delhi, we started in 1961, completed 50 years. We have relatively small size compared to other IITs. It is 320 acres. We have 13 main departments, including the science and engineering. We have 11 centers to do the collaboration with industries. And we have 3 schools, very specialized, sponsored by companies. And then we have about 8,000 UG and PG, the undergraduate and postgraduate and PhD. So some pictures of our campus. So this is our science and administrative building. And this is the greeneries of the campus. These are the houses and the student residences. Students and teachers all stay in the same campus. This is our library and our symbol, IIT Delhi's symbol. Now I come to my laboratory demonstrations. So we call it PAR, Program for Autonomous Robotics. It is sponsored laboratory by an organization, government organization called Bhabha Atomic Research Center in Mumbai. And we are 10 faculty members from mechanical, electrical and computer science. We have 20 plus students, and this is our website, robotics.itd.ac.in. First I will show you ambience of our laboratory here. This does not. Yes. Later. So this does not have sound, but later on I will have some sound also. So those are the 5 sub-projects we have it, and at the end of the project, 5 years, we have to integrate all of them. So we have a small laboratory here. So we have 2 industrial KUKA robots. I will show some experiments in the KUKA robot. One of them will be the paid in hole operations using vision. So we have a camera here. These are the small pegs, about 15 millimeter diameter, to be seen by the camera. This is a small new robot, a mobile robot we bought from KUKA. This is the latest one, not yet installed. At that time, KUKA lightweight robot, 7-axis, force control. This is exoskeleton. You can wear and you can control the robot. I will show you the video of all. Okay, I'll stop this and I'll show you some of the experiments. So let's see, the first one is called immersive This is a project by our computer science professor. You see, this is the real robot, the video signal. This is the CAD file. This is actually the virtual environment. And from the virtual environment, I can create a virtual environment. These are the small pegs. And then the person can control seeing this. So this is a remote operation, teleoperation purpose. So this person can see this environment and can control this robot. And to do this, you need a three-dimensional understanding. If you take only video signal, video is only two-dimensional. So it is not possible by a person to insert a peg. Here you will see a peg will be picked up and will be placed on the top of it for arranging. You see, so the person is controlling here using haptics device, and the real robot zoom in of this is coming here, and this line indicates the length, the distance calculated from the tip of the gripper to the object bottom. So this line shows the center, the blue line shows the center of the peg. So you see how smoothly he should be able to place it. If you take only video signal, we have only one camera. If you take only video signal, you need multiple cameras for stereo system. Moreover, there will be time delay, and so the control will not be appropriate. So for this reason, augmented reality facility has been created under this project. So I'll stop this. It will show another pellet on the top of this. So I'll stop and I'll take you to the next one. Next one is about a mobile robot. So it will do a formation control. Three robots will form a triangle, and then the centroid of this triangle will move along a circle. So it's a predefined path for center of formation as a circle. This does not have a sound, so I just switched it off. Another type of robots, mobile robot. This is an Indian company, makes robots for education purposes. So they are communicating. So this is a project from our electrical engineering department. Stop. So then I show you. So this is a pneumatic gripper, because if you use a mechanical gripper, it is very difficult to pick up from there, and this material is very fragile. It may break. Now a mechanical gripper will come and hold it vertically. So before it picked up, it has actually taken the picture of it and decided which pellet to pick. And now the mechanical gripper is coming. We are doing it very slowly for safety reasons. So this is a KUKA KR5 ARC industrial robot with a 5 kilo payload capacity. Now it will come here. This camera will see the picture of this tube. This camera will take the picture now. And then it will come close to the hole. And after that it will switch to a 4-stroke control, because the clearance is only 0.1 millimeter diameter. Diametral clearance is only 0.1 millimeter. So then it will switch to 4-stroke control. So it was the 4-stroke control was the work of a PhD student, Mr. Arun Dlhi. And the vision is the project from our electrical department. So 2 projects have been merged here. This is the vertical. I will show you the horizontal insertion. So I will show the horizontal now. Excuse me. Now I will show the horizontal one. So this is the horizontal. Horizontal is a little difficult. It will come. It will come. Oh, what? So now it is the horizontal one you will see. Horizontal is a little difficult because you have to push inside, because the purpose is to do the assembly task. So again the algorithm is the same, the force torque control. We find out the center of the hole by finding the minimum depth algorithm. And then after it is placed, you will see the gripper will have extra motion to push it. So a little fast I will go. Now you see it pushed. So we could successfully demonstrate both horizontal and vertical motion of this. The last of our project is the exoskeleton for teleoperation purposes. So this was completely designed and developed at IIT Delhi. So as you move the hand, the robot hand will be moving. And now soon we will have the force feeling. So when you lift an object, you will be able to see, you will be able to feel the weight of the object also. So here we are not able to do 0.1 millimeter clearance, but we could do in a big hole because it's still in the development stage. So I stop this one here. Okay, so that was about our the PAR laboratory, which started 5 years ago, and we are soon completing those 50 years. This is a collaborative work in the same laboratory with Prof. Matsumaru, started in 2011. We had our first visit, but first I will show you what we are doing it. This is a project from Prof. Matsumaru's presentations, what he does as image desktop projective arm trainer. So many of you may be knowing this. So this is for the training of arm for some persons who may not be very good in their hands, maybe some physiotherapy purposes. So this is a game you play, and you score some points. Of course it is a game, but at the same time you get exercise in your hand. So I stop. So after our first visit in 2011, we started discussing that how we should do the collaboration. Then I thought this is a good device for medical purpose, of course yes, but then I thought I can adapt it for education purpose. In India, as you know, there is a large number of population who do not go to school because of many reasons. One of the reasons, in my opinion, could be the school is not interesting. So to make the study interesting, we borrowed the concept. First I will show the video, then I will explain. So we call it SAKSHAR. SAKSHAR in Hindi, the Indian language, one of the Indian languages, means literate. So we want to make people literate. See this demonstration first. So very similar arrangement. We have a LCD projector. We have a laser sensor here, which places the hand position. And here I have 4 pictures. And on the top it says find P for pigeon. So if you touch pigeon correctly, you get a point. If you do not touch pigeon correctly, you get a chance, because there's a lining phase. Then we have another module called evaluation phase, where you deduct scores. So here Q for queen, or Q for Q. So this is the Q, so until he touched it, no, he could not get a score. And here is the time, the left is there, and that points it is score. So my understanding is, if you introduce this in the schools, it may become very interesting for the small kids to learn, particularly in villages where they find studying is boring, and their parents may like them to go to some work and earn some money. So we would like to take it to the schools, but the problem here is this sensor, it costs 80,000 yen, sorry, 80,000 rupees, so it will be 160,000 yen, so 16 man yen. Okay. So now we are working on a Kinect sensor. Last year one student visited this institute, and then Professor Matsumoto was very kind to share this Kinect with this boy, and now there is a girl working on it, and what she is working I'll explain briefly. So what do we want? We want to make any surface a touch surface. Okay? Maybe this surface a touch surface, maybe this surface a touch surface. Okay? And where do we want to use it? We want to use it to begin with in this kind of system. And so we are using Kinect, and the mathematics used is the regression analysis. And at this point what we want is, we want to detect the fingertip of this user using the Kinect. And we know that our intention is to touch. So we're going to touch, right? So the idea, we know that fingertip will go down depth-wise, and then after some time it will go up. So whatever cloud data we are getting, we are doing a curve fitting, maybe a second order hyperbolic curve, and from there we can trace out what could be the possible path generated. So here is this analysis done by her, and this is the explanation of this, and mathematics behind it, and this is the graph. So we could trace relatively correctly this touching thing through this regression analysis, and here when nothing is happening. So the analysis result. So we are yet to integrate with our game now, but I wanted to explain this. So she is Pratusha, she is working on it. She is a second year undergraduate student. In her summer work for 2 months, she will be working on this. So this is the Kinect, and here she is touching, and she is looking at the plots which is coming. So next page we would like to integrate with our game to see whether it is being correctly or not. And here we put this thing on a stand, on a tripod stand, but to have less calibration required, we are proposing that if we can make a table like this, I think almost minimum calibration will be required for the Kinect. So that was this work. So talking about collaboration with Waseda-IPS, particularly Professor Matsumoto so far, well, as I mentioned, 91 to 95 we worked together. 2011 Professor Matsumoto wanted to have collaboration. He visited to explain what he wants in 2011, attended the conference also,
2012, our first visit, myself and one of my students visited. That's the time we started what collaborative work we should do. Next year, as a part of Waseda-IPS symposium, again myself and Mr. Ribi visited. He got one of the best prize in the symposium. And then last year, only a student visited. He made a presentation of our collaborative work on SAKSHAR. He made a presentation in this conference. So the second laboratory which I work, which is not only robotics, other types of activities also, but the first one is kind of robotic application. It is a truck simulator. We know flight simulators. Every pilots have to go through a training in a simulator which looks like this. But here we like to train the driver of a truck, in the simulator. And first, the design which we have done, a prototype, physical prototype. I will show you first. So we at IIT designed it, and a company near Delhi, he manufactured it. So in the factory, this is the testing going on. It has servo motors, AC servo motors with a gear, and ball screw mechanisms which can do the linear motions. And this kind of simulator, which are also called the parallel robots, are better compared to the serial type robots because of their high strength to weight ratio and accuracy. So almost all simulators on the world are based on the parallel robot. Here we have a small interface on the computer to reproduce the motion of the actual simulator. I stop here. Before that, we did some analysis using a software. This is called ReDySim. It's a Korean software. ReDySim software. Again, we took the CAD file from the CAD design. So this symbolizes the motor, the ball screw. Here I am demonstrating only the particle going up and down. However, these parallel robots have more complexity in their kinematic analysis because they have singularities which are different than the serial robot. So recently one of my master students have finished the studies on the singularities. So the parallel robots have a singularity which are called the gain singularities. If you want to know what is the gain singularities, I will play the video here, just observe very closely what is the gain singularity. So it's a small prototype we made in the lab also, a very small baby simulator. You see, I will replay again. So after some time, it loses the control. Oh, okay, so that's the singularity actually. Now it gains extra degrees of freedom. You want to understand what is this extra degree of freedom? Let's play the other video. Let's stop this. Let's play this. You see, even though all motors are locked, but you can still play a little bit. So in actual applications, you must avoid that zone, or you should have a path planning. You can cross the singularity without losing the control. Okay, so that is the analysis done by this MTech student. Okay, that I will demonstrate a little later when I come to the dynamics. Oops, came to end. I do not end now. Okay, so that was about the parallel robot. We also worked on haptics devices. Okay, so now I will demonstrate a haptics device. So here, 1 degree of freedom haptics. So you want to define. So this is simple a rotary joint. I define a wall here, virtual wall. You see, you cannot move it. No? I can change the wall anywhere I like. So this is 1 degree of freedom. We are using FPGA to introduce the stiffness and etc. In this single degree of freedom. Then I stopped. Then we created a 2 degree of freedom also for medical simulation purpose. So here is a 2, again a parallel manipulator type of thing. Here at this junction, we have defined a virtual wall. So the person cannot move. In fact, there was a sound also would be coming. I don't know if this would be there. So here, you see, if you change the stiffness, you get a different sound. Here, different, right? So you change the hardness, you get the different sound also. So recently a PhD student has completed his work on this topic, and it was a joint work between 2 IITs, IIT Delhi and IIT Madras. Since I am a mechanical engineer, okay, so I wanted to apply in education. So let's see how haptics I can apply in education. Okay, so here I have a series of systems. Let's start with say pendulum.
Example of a pendulum and a prop, it's a simple pendulum example that we can also feed with the device. You can change the mass of the ball here.
So you can feel the weight of the ball at the end. You see, if you leave it, it will look at pendulum motion. So here you can feel.
Example of a pendulum and a prop.
So the idea is in a mechanical engineering class of mechanisms, we can see the motions. What about the dynamics? If you want to feel how much force I need to lift it actually, right? So that feeling we can introduce here. So I have another simple system which is called forward linkage, which is the basic. And since this has only 1 degree of freedom.
So this is a 4-bar mechanism whereby the haptic device being manipulated by an operator is a 1 degree of freedom system, and corresponding animation is reflected on the screen, which is generated with OpenGI.
So what is happening here is, now of course this has an encoder, and that encoder motion is going to the animations here, but the whole dynamics is actually getting calculated in a MATLAB program, and you can feel the force. If you rotate it faster, you will find it is difficult to rotate it. Okay, so that's the feeling. So not only the visual feeling, the motion, but we want to give you the dynamics feeling. So we feel this haptics not only for medical applications or other applications, but in education also it can be applied very conveniently. Now suppose if you want to have more complex systems. So here we have Stewart platform. Now Stewart platform has 6 degrees of freedom, but our device has only 2 degrees of freedom. So you can control only 2 motions. It's not very clear on this projection screen. Actually, yes, the blue one is the top platform. So since it is a 2, I can move in a 2-dimensional force. So I can move on a plane by this 2 degree of freedom device, and I can feel the force on those directions. Okay, and then you can change. So it is just a demonstration. If you wanted to feel the complete dynamics of the 6, you need a 6 degree of freedom here. But we wanted to demonstrate that even with a 2 degree of freedom, you can feel at least any 2 of the complex system. So that was the idea here. So that was now I have an interest with educations, as you can understand by now. The engineering education based on the blackboard or whiteboard or LCD projector is very boring to me. I don't like. As a student, probably I didn't like, but I had to force myself. So I wanted to create new ways of learning. Okay, so here I have a demonstration of new ways of learning. So just watch first.
And we subject and I use for
is a robot game, robot playing badminton. Could not pick up. So this is called a RoboCon competition, very popular in the Asia Pacific region, particularly the Japan, China, Indonesia, India, Singapore, Hong Kong. So actually it is an Asia Pacific competition held every year in the month of August. So this year August, Indonesia will have the final competition amongst about 17 to 18 countries. But we organized a domestic competition first. About 89 teams participated. And the champion will represent India to Indonesia. Okay. Now, I have been helping my students for the last 10-12 years to build these robots. Okay. But after building these robots, I asked myself these questions. After that, what? No? The what answer is as follows. When they build a robot, they are in a hurry, kind of in a hurry. So they do not apply, or they do not have the time to apply all the knowledge which they gathered in the classrooms to build these robots. So after the robots are built, when they come back, I ask them, has your robot failed? If the answer is yes, now find out the answer from your textbook knowledge. You can take a project. 3 months project, 2 months project, 1 year project. If it has not failed, can it be improved further? Right? Develop some software. Okay? So that is the way we impart the education, and I find this kind of education is extremely fun and rewarding. Okay? And I call this concept as a ROCB, Robotics Competition Knowledge-Based Education in Engineering. And yesterday I have gifted one book which we have written with a student to Professor Masumaru's students' laboratory. If anybody is interested, they can visit that laboratory and have a look. Otherwise, just search for Google search called ROCB, and I think it will come. So it is called ROCB. Schemes Robotics competition. That means the knowledge you get by participating in robotics competition. Knowledge based education in engineering. Okay. Robotics knowledge-based education in engineering. So that is one of my favorite subjects these days. How to make it popular amongst people. Now the next part may not be very easy for non-mechanical engineering students and professors here. So I will make a simple explanation using knowledge of our high school knowledge, that what I do as a dynamics. So DeNOC is an abbreviation of Decoupled Natural Orthogonal Complement. It is taken from linear algebra. Means decoupled natural orthogonal decoupled natural orthogonal complement. So DENOC. This is used in linear algebra, that if A, B is equal to 0,
B is the orthogonal complement of A. And similarly, the A is orthogonal complement of B. We compute one such matrix during the dynamics naturally. So we call it natural orthogonal complement. It was a method started by my PhD supervisor in Canada. And so that was his start, and then I have added the D part. Anyway, so let me explain what it is. The NOC part was my PhD work at McGill. So when I was using this method for the modeling of space robots in Toshiba, that was my task given to me, that do the dynamic modeling of space robot. I had some difficulties here using the NOC. So then doing some research, I found that if I use decoupled form, I will explain it later, then you can do the simulation quite well. So 1995 was our first publications. Then I went back, so we developed a program for industrial robot. Then I have used for parallel robot. So that was my research work in Germany as a Humboldt Fellow in University of Stuttgart. Then we started using it for our courses. The ReDySim is actually the origin of our RoboAnalyzer software. So 2003, but it was in Linux. People were not using my program because everybody uses Windows. Almost 90% people in India uses Windows. So I had to change it. Then I had the opportunity to spend 2 months at McGill again. So there I guided the master students for parallel. Then this has an application in machine tools. Production engineers, so they use it. So there's a PhD student. Then it was applied for general closed loop systems like simulator, and for villages we have did some modeling. So there is a book by Springer from the thesis of the student. Then the RoboAnalyzer has come up in 2009. Then I had a student from Bosch, India, who was working on diesel engine. So we have used for CAN mechanisms also. Then finally that ReDySim has come out. ReDySim has come, and that was another PhD thesis, and that is another book. So that book is with me if you are interested to see the second dynamics of tree-type robotic system. Okay. And then people have started working on flexible bodies, but they do not have to do the extra calculation using finite element. So they can do with the rigid body modeling. So there is an example I will show you at the end. And the latest one, this year, one student has submitted a thesis. So that is the history of the dynamics. To tell you simple what we mean or what we do in this dynamics. So this is the first paper I just wanted to show you. It is available in 1997, IIT Transactions on Robotics and Automation. So the theory is from there. But the first presentation was in Nagoya, in ICRA. In dynamics actually, what we want as a robot controller, so we talk about two main problems here. One we call it the inverse dynamics, which is used for control. For example, I want to move this end effector along this path, and maybe some forces are coming. Maybe I am washing or I am cleaning this wall of this table. I want to calculate that how much torque will be required by the motors placed here. So this is find the joint torques for given joint motions and end effector momentum. So we calculate this. That's called inverse dynamics. We have another problem called forward dynamics. Suppose you don't have the robot with you, okay? But you want to know that if you had the robot, how it will move. So if I apply this torque, how it will move. Suppose you want to buy a robot tomorrow. So you want to study that whether it will serve your purpose or not. So we call it a forward dynamic. And this is used for simulation purpose. All software actually are based on forward dynamics of system.
could be a robot, could be car. So here is a simple demonstration. I repeat. Okay. So what is the meaning of inverse dynamics and forward dynamics? So here is a simple demonstration. If I have a mass m on the top of a table, and if I apply a force, it has moved to distance x. So if I ask you a question, right, that can you calculate that what distance it has moved, or if I ask you the questions, how much force is required to move that distance x? Okay. So let's answer the first question. If I wanted to calculate what distance it has moved, you can do some experiment. You can apply, you can attach some sensors and attach to a CRO, okay, to see how much distance it is. I say, sorry, I don't have so much money, or I don't have time, right? Can you still do it? The answer is yes. So I do the modeling. So modeling means I write Newton's second law, which we study in our high school. Force is equal to mass into acceleration. Okay, so this is called modeling. And if I wanted to know where it goes, so what I do is I calculate x double dot as F by m. Because m I know, F you have told me that I have applied 10 Newton or 100 Newton. So I calculate this. Then I know the initial positions, I can integrate it to get the velocity. I further integrate to get the position. So after time t, I know that where is this mass is moving. So that's forward dynamics, as I told you. These integrations are simple integrations. Together they call it simulation. If I ask you the reverse question, the opposite question, right? If I want to move x with the time t, how much force will be required? That's very simple. You told me time t, so I can calculate the velocity by differentiation. Another differentiation, I can calculate the acceleration. Mass I know, I multiply, I get the force. Okay? Generally, this green problem, the inverse dynamics problem, is simpler compared to the forward dynamics problem because it involves integrations. And for complex systems, you can imagine simple integrations will not be possible. You have to do the numerical integrations. Okay? So that's the whole story of dynamics, what we do. Now, if I bring the concept of NOC, how it is different. The NOC concept tells that first you do not think that this is on a table. First think it is a free body moving on a space. So then I can write all the external forces, all the reaction forces on the table are equal to mass and into this the accelerations. Now please note, since it is moving on the body, that acceleration cannot be any directions. Acceleration has to be in these directions because this is the motion I want. So the motion, the velocity is equal to the direction I and x dot. Okay? So if you combine these two information, so what we do is we pre-multiply this I with these whole equations, and if you simplify, you get the same Newton's equation. So the idea is for a complex system, you first make it a simpler system, okay, of this kind, okay, and then find out what are the equations and multiply. Let me repeat interpretation. For example, I have this book, okay, I have this book, okay. If I apply a force here, all forces will convert into motion. If I apply a force like this, it is not moving, right? So all force is getting converted into reactions. If I apply a force like this, what will happen? Some portion, this component will move it here, and the vertical component will create the reactions. Since I am interested only in the motion part, that how much torque will be required, so what I do is I do the projection of the whole motion to the direction of. So this is the geometrical interpretation of the dynamic equation, that I do the projections of the whole motions on the possible direction. So that is what it means. So whole my NOC or DNOC is based on this concept, but I will not give you much further details except some equations to tell you that okay, the complexities involved only. So now if it is a spatial motion, You have a rotational motion for which you write rotational equation of motion, and then you have a linear equation. You have a linear equation of motion. You can combine them in a matrix form. There will be 6 equations here. Okay. Now what I do is, for a serial robot, I have separated the bodies. Let's see, no joints are there. I have removed the joints. So body 1, body 2, body I, body N. So I write all equations, and all equations can be put in another big box, in this case matrix. So just like when you travel, what you do, small pen, pencil you put under a small pouch, and that pouch in a small bag in a suitcase. If you are going abroad, with your whole family moving, then you put it in a cartoon box. You do the same thing. Scalar equations in a vector equation, small vector, big vectors, right? Now it is easy for us to understand the concept. So this is a big equation, 6n by 6n. Now the bodies are separate, but actually they are not separate. They are bound with something. So this binding we write again in equation form. The angular velocity of this body is equal to angular velocity of this plus whatever the motor motion coming here. So this is here, theta dot. Similarly for linear velocity. Okay. So again you put in a box, big box. So here is the big box now. So all the velocities of the bodies is equal to all the motions coming from the motors, and of course this matrix N. So that was my supervisor created, NOC. But I realized when I work in Toshiba that if N can be written as NL and ND, what's the meaning of NL and ND? NL, it looks like a lower triangular matrix, and ND looks like a diagonal matrix. Then many things simplifies. More than simplification, more interpretations are available. I will give you one such interpretation later on. But this is what we get. We started from here, pre-multiplied. So this is the equivalent to pre-multiplication that I have written it here. N transpose WC is equal to I transpose what I did earlier. And then this equation is actually this, the small equation. So there is a equivalency for you to understand easily. And this equation we call the Euler-Lagrange equations of motion. Okay. So I think with this much information how it is happening, I will not go to further details because that's multi-body dynamics research. One easy thing is the elements of I can write in a very systematic manner in the form of small matrix, small vector, small matrix, small matrix, small vector. A normal researcher will not get this. They will just use the computer and get them as a number. And if you get them as a number, you lost the story inside. Just to give you an example, what story I am talking about. Suppose if I tell you, please calculate a square plus 2 into a into b plus b square. I ask you, please calculate. Okay, of course, we know how to calculate. If I ask you, how many computations you have performed? So if you note, a star means a into a. So you have performed a multiplication. So here you have performed a multiplication. Okay, you have performed a multiplication here. You have performed a multiplication here. You have performed a multiplication here. You have performed an addition here. You have performed an addition here. So total how many multiplication and how many additions you have performed? 1, 2, 3, 4. 4 multiplication and 2 addition. Okay? But all of us know, what is this? This can be written as A plus B. Right? So if you know that this is this, then you perform one addition and one multiplication. Is it not a saving of your computer time? Right? Almost almost one fourth of your computer. 4 multiplication, only 1. Addition 2. So my intention is that if you do not perform as a number, okay, try to keep it as an expressions. Then I know this expression is simple in this form, a plus b whole square. So that is my intention there. So when I write a I, ij,
if I write Iij, not calculate as a number, so I can get lot of information similar to this one. And that makes my algorithm very efficient and very numerically stable. Okay, so saying that, I have solved a simple system for you that how to calculate that inertia. So these are the several vectors. So this is 1 degree of freedom robot arm. So you can write E means it is an axis of rotation. It is 0, 0, 1. D is this vector. A is the length. Half of A cos theta, half of A sin theta, and 0. I2 is the inertia matrix of this link. A slender rod, you can write in this way, and then you do, finally. And this is well-known thing for us from our first year of engineering. We know that a slender rod, the mass moment of inertia of a slender rod about its vertical axis at the end is m square by. So using a systematic approach also we can get the results. Similarly, for each portions it will be 0, tau 1 will be this one, and the final equation of motion is this, which we can calculate very simply also, but here I have shown the steps for doing the calculation of complex robots. So this algorithm is written in my book. So I have a copy of this book today, and this I will hand over to, this is the second edition of my book. I will hand over to Professor Matsumaru for him to share with others who want it. Otherwise, the Kindle version is also available in Japan. I have seen yesterday only. And the soft copy is available. The first edition, which came out 2008, has translated in Mexico, in Spanish. And in China, some machine corporation, I think the Chinese students can understand. Some machine corporation in China, here it is written, they have published the book in China, but inside is all in English, only outside covered is in Chinese. So the whole algorithm is there, and with the example of the software, I will take little time, 3-4 minutes to explain the software part. Not the dynamics, also the kinematics we are doing. Let me up the software. And the software is free. For me, the philosophy is make the knowledge available free to the students of the world. So here, by default, a 2 degree of freedom robot appears. So if you wanted to know forward kinematics, you click forward kinematics. Now, forward kinematics means given the geometry of the robot, you try to move the joint 0 to 180 degree, this is my first joint, and 0 to 90 degree, the second joint, and you can see the animation very smoothly. Okay. Now, we teach DH parameters in robotics, okay, and it's extremely confusing for the students. So if you want to see the DH parameter, and here there is a small icon appears here, screen resolution. Screen resolution is here, show here. So joint offset, show the joint offset. So this joint offset is 0, so nothing. So let's change joint offset to some value, say 0.1. So this is actually has changed that in the file. So this is the meaning of a joint offset. Okay. So then link length. What is the meaning of link length? So this is the meaning of link length. The joint angle. Since joint angle is 0 here, the meaning of joint angle, if you press, so it will show the meaning of joint angle. And if you wanted to show the meaning of all, so you can show all. As it changes the frame, it will highlight here. So this is 45 degree, the first joint, then this is link length, then twist angle is 0, but you can change the twist angle actually. I will do it after this. Then this is 0, variable, then this is 0.2. So the concept of DH parameter can be visualized using this tool.
If you change the twist angle, say 30 degree, no, and 30 degree, so now you can, so this is the meaning of joint offset, the joint angle, the link length, and now this is the twist angle. No? So instead of parallel, you have made it twisting. So this is only for 2 degree of freedom, but we have 6 degree of freedom also. Then you want to do inverse kinematics, okay? So if you go to inverse kinematics general program is very difficult. So let us take the same robot. So I have some input here. So it has 2 solutions, okay? You want to see the solution, show me the first solution. It has shown the first solution, okay? You can take the projection, say top view, okay? So this is the meaning of the one solution. What about the second solution? Show me the second solution. Show me the second solution. You see? So this is the meaning of inverse kinematics. So the same position you can go 2 ways. One this way, another this way. Okay? So concept of inverse kinematics is generally difficult. What are those? So here we are giving a demonstration of the physics or the geometry, right? Before you learn the mathematics of it. So my message is learn the physics and geometry of the robots first. If you find the subject is difficult, then you learn the mathematics. You want to move from the first solution to the second solution. So what I did, I have populated the 2 solutions here and ran forward kinematics, and then I can see. So it starts from the same. And then if you want to see the end effector configuration, there is a small d, but this homogeneous transformation matrix will show up, and here my resolution is here. So here update, so it is updating. Okay. So now you want to do for more complex, say 6 degree of freedom. You have seen the KUKA robot earlier, so let's say KUKA robot, and whole CAD file will come. Let's see, isometric view. It does not come yet. Okay. So all the 6 will come. Okay. Now again, if you want to do inverse kinematics for such robot, it's not so easy actually. So you have to so inverse kinematics. So you have to choose from here. We do customize also. Some company has given us their CAD model. We have done for them free of cost. So here we have KUKA KR5R. So if I ask you how many solutions it has, the answer is there on the screen. It has 8 solutions. Okay. Now what are those 8 solutions? Let us try to visualize those 8 solutions. Let us show the first solution here. Okay. And first solution here. So show the first solution. So it has shown the first solution. Then show the 4th solution. Show the 4th solution. Now both are the same actually. Okay, that you can confirm from the configuration. If you see this matrix, now I wanted to take the solution from 1st to 4th. Show me the motion of the thing from solution 1 to solution 4. Okay, and then okay. Now I do the forward kinematics. So cancel. Sorry, so this I'm just. So you can see the motion happening. So inverse kinematics, and this KUKA KR5R, and I wanted to do inverse kinematics. Solution 1 to solution 4. Okay, and then I do this. So this now it's a forward kinematics. And now you can run. Now you will see that it is moving from solution 1 to solution 4. The position and the orientation all same. Okay. You want to do the dynamics because I was talking about dynamics. Okay. You wanted to understand that if I let this robot fall free and no motor, action, what will happen? So you can do forward dynamics, free falling, and it has done, and see this what it will do. Okay. Of course, no collision is there, so it will show you how it will move. So the study of robotics has become very simple, and we have some more industrial robots as well, about 16 or 17 of those. So those you can do the trajectory planning as well, like we have ABB, Kawasaki, Fanuc, no? So let's say this is ABB robot, and you want to do just like a, this kind of thing, or you can have a Cartesian planning and also. So RoboAnalyzer now has an interface with the MATLAB. There is an Australian professor named Peter Cork. Now he has a robotics toolbox in MATLAB. So now we have an interface with RoboAnalyzer. The graphics can be seen in RoboAnalyzer, and the calculation can be done in robotics toolbox. Okay. Now that was about the serial systems. Okay. But now what about the closed loop system? Okay. Or the tree type system. Here I wanted to tell you a small joke. It will take about 20 seconds or 30 seconds. It will be kind of a break, from monotonous lecture. Okay, let me share a joke first. Okay, so there is a boy who studies in class, say 8 or 9, high school, okay, or middle school. He was preparing for an English examination in the next day. And English examination, he knows that there will be a question on writing an essay, description about certain topic. And he thought, I have no time to study so many essays. So he thought, essay on cow is very important. So let me memorize a cow essay. Okay? So he memorized cow. Next day in the exam, the question paper says, write an essay on river. So he was a little puzzled. He thought, I prepared on cow, how can I write on river? But he is a very smart boy. He started writing that I live in a place close to a river. Both sides of the rivers have very fertile soil. Okay? Many green grasses and vegetables grow on the sides of these rivers. And many animals come to eat those green grasses and vegetables, like horses, goats, cows, buffaloes. Cow is a domestic animal. Cow has 4 legs, 2 ears, and then it is a cow essay, right? So here I thought, I am very good in serial systems, right? But not so good in tree type system, okay? So then I remember the cow essay. So how can I write the cow essay, okay? So soon I will show you how I wrote my cow essay. Okay, that is the serial system, okay? So let me show how I wrote the cow essay. So you see, this is a tree, one branch, this is another branch. So these two together makes a tree, right? So this branch, or you go back, this branch is like a serial system. This branch is a serial system. This branch is a serial system. So I know the serial systems, right? Now how can I make that tree type system into serial system? Then I can write my cow essay, right? So I do exactly the same thing. So I treat this as a serial system, this as a serial system, this as a serial system, and I do a little bit of mathematics here to connect them properly so that it becomes like a tree type system. Okay, and the story is complete. Now it is a closed loop system, right? So this is closed, right? I said if it is closed, why don't I cut it? Right? I cut it here, right? But cutting it mathematically means something, so I introduce the something, right? So the cutting means I remove the joint from there, right? If you think in terms of force, then what is the joint? The joint means two forces coming together. I love you, right? So they are staying together, right? So two bodies do not want to separate. So the force of attraction is making them stay together, okay, or rotating. So this is the force of attraction, no? We call it Lagrange multipliers. So we do this, and my cow essay is complete. So if it is a close, first I make it open. After opening, I make it tree, and after making a tree, I go to serial. and the story continues. Okay, and of course mathematics becomes a little lengthy, but at the end I get a similar equations of motion what you have seen earlier. So in summary, when I talk about DeNOC method, what did it do? It writes the velocities of all the bodies in terms of the motor, or what we call the independent coordinates. Okay? Then we write the free body diagram or the Newton-Euler equation. We pre-multiply the transpose of that thing to get the minimum. Okay? Now for this we do the calculation similar to what I have just shown you here. Okay? So I did the calculation of how many multiplications or how many additions I am doing it if I have to do inverse dynamics. If I have to do a forward dynamics, how many operations I am doing. You see the bold line is ours. Only in this case we are the same as one of the cheapest available in the market, but all other cases we are the lowest. Generally I tell my students, no, we generally want to have more things. We want to have more money, more houses, more cars. We do not prefer less. But this is one example when we prefer less, right? Less time, right? So here it takes a less time. Okay. So now this book I have already talked about. It cost about 10,000 yen, about €100 or $100, very expensive. This gives you all these examples mentioned here. Again, my concept is to give this knowledge free. Book is not free because it is published by them, but the software is free. Now you can download. From here also we have a link, but we have a separate website maintained, redysim.co.nr. Otherwise from here also you get the link. Just to demonstrate some example. So first I do a gripper, 1, 2, 3, 4 links gripper. We analyze in ReDySim, and this is the animation of the gripper. Okay. This website will talk about how to use. I repeat. So this is the gripper. Then planar biped. Planar biped. So this is a planar biped. Okay. So here we use working algorithms, the ZMP, zero moment point, and all those things. Then we are not happy with the planar only because actual human beings are spatial. So it's a spatial motion here. So here we have a control also, otherwise this guy will fall. Then 4-legged robots. The 4-legged robots, okay. Then the 6-legged robots, tech support. So these are all done, and once you download the ReDySim, some of these examples are inbuilt. Now here one of my colleagues from another IIT, IIT Madras, he was trying to model a rope or chain. He was trying to mainly rope he was trying to do it, and he found out this knowledge of multi-body dynamics considering the rope consisting of very small rigid bodies and connected with some joints. And you can apply a serial robot knowledge like a cow essay, and here is the results. So he was using a software, commercial software, which was failing after 200 degrees of freedom. And for our paper 2013, we have gone to 100,000 degrees of freedom. It took us 17 days to do the calculation. So now I wanted to tell you the closed loop, right? Because I have to complete the story. So this is a planar parallel robot making a circle. I mentioned about the singularity, right? Let's see if I wanted to overcome the singularity. So again the same. So that same MTech boy has studied. So this line is a singular line, the red line. Okay, and I'll do this animation for you. So this is a singular line, and at this juncture, the torque requirement is very high. Right? If you ask the motor to run, motor will burn. generally there is a safety switch. No? So after this, animation does not go, no? Because the robot cannot move after this, loses its control. Okay? But using dynamics, I can overcome this control, and these are some of the calculations of using dynamics. So now you will see that it will cross. At this junction there was a singularity. Now it just passes. It's like give a little push. When there is a singular, it's like a natural vibration, no? High amplitude, no? You go at high speed and cross. Here what you do, as soon as you have singularity, I give little extra torque to the motor. Something like this. Otherwise you will fall, no? So that's the kind of thing. So that's for the planar. But then I have for the spatial also, I want to go from here to here. And this is starting point. This is the singular point. And this is the final point. And now I move. So you see both the motion. So here you will see the robot will come and here you will see the robot comes and stops here. But same robot, same path, only the trajectory is different. But here it is moving very smoothly, no problem. So you can cross the singularity using the dynamics. Okay, these are more examples, so that part is gone. Okay, now the last part, another 3-4 minutes. So multibody dynamics, robotics, I was doing it for many years. Since 2003 or 4, I found out that my knowledge is not taken by any company. No? It's only for the education, that's fine. Whereas there is no company works for the people who work in the villages. For the big companies, no, it is somebody is working for the university is working, but for the people in the villages, nobody is working. And I had a project at that point of time to develop several machines for carpet weaving and cleaning. So this is the way the people do the carpet cleaning after a carpet is woven. So I thought, let me help them design it. So here is one such a design. So this is a carpet cleaning machine we developed at IIT Delhi. And after this development, we found it has a lot of vibrations. Okay? So since my knowledge is dynamics and also robotics dynamics, so I thought, let me analyze it. So now you see the same mechanism. Actually, I have cut it several places and made it look like a serial or the tree-type system. Okay? And we published in SME Journal of Mechanical Design in 2007. And then we did the calculation of all the results, and this is the how much is the torque required. Now you can see the torque requirement suddenly increases and suddenly goes to negative. We understand that there is an obvious reason for the vibrations. No? Suddenly goes high, goes down. Okay? So we said, okay, let us validate our results using a commercial software. So there's Adams is a commercial software used by almost all car companies. So we developed this model, the same, we call it carpet scraping machines. And these arrows are nothing but the force directions. So I stop. And our results are compared here. So one is our algorithm and another is the Adams algorithm. Now interestingly, 2007 or 10, this mechanism we found out from an Italian professor. He has used as a robotic leg. Okay? And this we have analyzed in our ReDySim. I showed the animation here. You see? It is exactly the same mechanism. If you wanted to see how it is same, you just compare. Okay? I don't have the picture here. Otherwise, this motion is approximately a straight line motion. If you see, it is approximately straight line motion, then lifts up and comes back. Goes straight, comes up, goes straight. It has 7. And here also, if you look at it, it goes straight, goes down. So the curve I have shown you this, you just rotate it by 180 degree and this is the curve. For him, he put the mechanism on the top. For us, we put the mechanism at the bottom. Very interesting. The same mechanism which we did not know. We use it for robotic carpet scraping machine. And here is a professor who is a robotic leg. The professor I know, Marco Ceccarelli, in I think Italian Institute of Technology, most probably. So here I close saying the conclusion. I have explained about robotics activity at IIT Delhi. I explained DeNOC in a simple manner for serial robots first, the RoboAnalyzer, and 3-type robots using ReDySim, and how this concept can be used in Mudra. Mudra means multi-body dynamics in rural application. Mudra also means in Indian languages means money. So you can save money or you can earn money if you can do the designs. Mudra also means some postures. We have yoga very famous. 21st is the International Yoga Day for your information. June 21st. Last year UN has declared this. June 21st is International Yoga Day, and it will be celebrated all around the world. So in yoga there are some postures, right? You can sit like this, you can sit like this. Now it has benefits like improving the concentrations and other things. Without acknowledging our families, I think we cannot do so much work. So that's me and my family, my students. That's Arun who visited here, Ribi also visited here. And also thanks to Professor Matsumaru for inviting me here, his students, my students who are interacting, and of course our institute. And finally I wanted to share two conferences. One conference is almost, you cannot submit paper anymore. It is July. We have a Robotics Society of India, Advances in Robotics, every biannual conference. The next one will be 2017. But this one, if you deadline is gone, but if you plan to visit India, December is a very nice time to visit India. I can still ask the organizer to allow to submit the paper. It's an IIT Kanpur. It's about 400 kilometers from Delhi. It's about 1 hour flight. So with this, thank you and arigatou gozaimasu. If there are questions and comments, I think we still have about 6-7 minutes.
Yes, okay. So it's a good chance to maybe some of you not familiar with dynamics or physics or something, but some kind of part you can understand maybe.
Yes.
So please raise your hand if you have some comments or some questions. Yes, please.
Yeah. Please, you can ask other questions also, non-technical.
Non-technical.
Also, how is it in India? What is the temperature now? Yes.
Thank you very much, Professor, for the lecture. I noticed at the earliest at the slides, you mentioned about the vertical motion and horizontal motions. So I noticed the mechanism of picking up the bar, the little bar, and plugging inside the tube, and then the bar locker let the bar
Push.
yeah.
Yes.
So can I suggest from a simple theory that between these pickup bars we can use additional air pushing?
Yeah, we did it. I have not shown it here. We have two methods. We have a air push also.
Yeah.
We did it that also. I have not shown in this video, but I have another video where we pushed with the air.
Yes, I think that
Yeah. We did it. We did it. Thank you. Any more? weakness.
It's
I think people are hungry, maybe.
okay.
Maybe. Okay. But my email is there, so you can write. It's there, but I can write it here also. So please feel free to write whenever. My website. I made it simple these days. And I would request, if you use the RoboAnalyzer, please give a feedback. Online feedback is there, and it is our utmost interest to make this product available free. Even though I get a contact from commercial companies to eat it, no? To grab it. No? But I told them I can earn some money by giving you, but some portions have to be provided free. No? Then only I can discuss the commercial part. No? Otherwise, because MathWorks is very interested, because they have robotics toolbox from Peter Clark in Queensland, but his presentation, his graphics is not good. So our graphics is very good. No? And sometimes I get comments from people because there are 4 or 5 such products available around the world, right? So they say, why you want to develop? Well, if it is so, then my questions to them is, their father knows how to drive a car. Why they want to learn driving a car again? Or maybe their brother knows how to drive a car. Why he or she wants to drive a car, right? We all have their desire to create something different, right? So here is my desire to create a software of our own and understanding the need of my people and the people whom I interact, right? So that is my answer to them. So if you have that answer, please do not go by that answer all the time. Please, whichever you feel important, you must do it. Okay?
Yes. So thank you so much. And
thank you very much.
Thanks again. Yes.
So I wanted to give this book to Professor Matsumaru to share with you.
Yes. Thank you. Thank you so much. If you are interested in, I have this book, so please come to me and watch this. Okay.
And this is 100 euro, so I cannot give you. But if you want to see, I'm here next 5-10 minutes. If you want to see, so please see. Okay, thank you.
Hi, thank you again.
Yeah, thank you.
The course students, so prepare for the report of this class. So until next week, I will repeat. Okay. Yes. That's all. So thank you for your attention and see you next week.